All right. So 8.6 on parametric equations, last section of Trig. And this section has nothing to do with polar equations. It has nothing to do with complex numbers. It's just sort of an oddball section they, I think, kind of throw in with the rest of the kind of leftovers from chapter 8. But anyway, this is an important topic. In fact, it's a topic that I wish the book spent a little more time on, and I wish we had more time in the course to really talk about parametric equations. But I'm just going to give you sort of the basics that you'll need for calculus. And specifically, you won't, to tell you the truth, you won't really see this again until third semester calculus. So, so let's get into it. So just to give us a little bit of an introduction, I'm going to use the symbol R to represent the set of all real numbers, and this is a symbol that I'm sure you've seen before, right? It's a common way to say all real numbers. So R is the set of all real numbers. R squared is the set of all possible ordered pairs, where the coordinates are real numbers. R cubed is the set of all ordered triples, and in general, Rn is the set of all n tuples. Well, so the reason I'm bringing this to your attention is because we could look at functions of higher dimensions, right? Like so far in your math experience, you've really only looked at functions that go from the set of real numbers to the set of real numbers. And when we graph these kinds of functions, we graph the inputs on one axis and the outputs on the other axis. So the inputs are graphed on the x-axis and the outputs are graphed on the y-axis. And so you get these two-dimensional graphs. However, in third semester calculus, you're going to examine functions of the form r to the n, functions that have inputs that are n tuples and outputs that are m tuples for any dimensions n and m. And this will come up again in linear algebra as well if you go on to take linear algebra. If you think about graphing these things now, now here you needed 2 dimensions to be able to graph your one-dimensional input and your one-dimensional output. Here you would need n plus m dimensions in order to graph this function. N dimensions for your input and m dimensions for your output. So for example, if you wanted to graph something, so if you wanted to graph, in here I said 5-dimensional space, so if you wanted to graph something like f going from r squared to r cubed, then in order to really graph that function, you would need 5 dimensions, right? 2 for the input and 3 for the output, which is not possible. Okay, so getting a visual understanding of these kinds of functions is impossible. But one thing that we can do to sort of visualize the functions is to ignore the inputs and just graph the outputs. Okay, so to see what I mean, let's say that you have this function f that takes a one-dimensional input t and maps it to a 2-dimensional ordered pair, 3 times t and then 2 times t minus 1. So this gives you a set of ordered pairs. Now, in order to fully graph this function, you would need 3 dimensions, 1 for the input and then 2 for the outputs. But we're going to ignore the input and we're just going to graph the outputs. So it says graph the outputs for t equals -2, t equals 0, and t equals 1, and then make a conjecture about the shape of the graph. So, so when I plug in -2, f of -2, I'm going to have 3 times -2, comma, 2 times -2 minus 1. So I get the ordered pair, -6, and then -4 minus 1 is -5. So I get the point -6, -5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. That's that point right there. When I plug in 0, f of 0 is going to be 3 times 0, comma, 2 times 0 minus 1. So that's going to be the point 0, -1, right there. And then when I plug in the point t equals 1, I'm going to have 3 times 1, comma, 2 times 1, minus 1. So that's going to be 3, and then 2 minus 1 is 1. So it's the point 3, 1. 1, 2, 3, 1. That's that point right there. And it looks like those all fall on a straight line. So my conjecture is that the shape of this graph is a straight line. Okay, so if we connect the dots, right, then they go kind of like this. So it looks kind of like a straight line. Okay, so again, note that we haven't graphed the actual function. That would require 3 dimensions. Okay, but what we have done is we've graphed the outputs. However, the input t does sort of make an appearance as an orientation, which we can indicate with arrows. Okay, so what I mean by that is when we plugged in -2, we were here. When we plugged in 0, we were here. And when we plugged in 1, we were here. So it seems like the points are sort of traveling in this direction. Okay, so that's the orientation of this graph. So so these parametric curves, the parameter t, it can still sort of make an appearance in the graph just by looking at just by marking the orientation on the graph. And that's what parametric functions are, or parametric equations, right? So a parametric function is a function that takes n tuples as inputs and maps them out to m tuples. But it's a function, it's one of these functions for which only the outputs are graphed. The resulting curve is called a parametric curve, and the input variables are called parameters. Okay. In this class, we're only going to talk about parametric functions of the form that take a single input and map it to an ordered pair. Okay, just as we did in this example up here. When you're looking at that specific case, those curves are called planar curves. The resulting curve is called a planar curve because it's 2-dimensional. And also in this case, you only have one parameter, t. Okay. The outputs are ordered pairs whose coordinates are functions of t, and so I sometimes write them this way. I say f of t is the ordered pair x of t, comma, y of t. Those functions, x of t and y of t, are called parametric equations. Okay. I don't think you're going to be, like, I'm definitely not going to write a test question that says something like define a parametric equation. But I am just explaining, what parametric equations are so that you understand, the title of the section and everything. And I do want you to know how to deal with parametric equations, graphing them and so forth. So this first example says, graph the following parametric curves and indicate the orientation. So we're given our x coordinate and our y coordinate as functions of t. And we want to graph this thing over the interval -2 to 3. So t is going to be between -2 and 3. This little symbol right here just means that t is in the interval -2 to 3. You've seen that interval before, or that notation before, but just to remind you, that means in. So t is in the interval from -2 to 3. So what I'm going to do is just kind of plot some ordered pairs. So I'm going to have my parameter t, and then I'm going to have an output that corresponds to my x coordinate, and then another output that corresponds to my y coordinate based on the values of t. And a good thing to do would be to plug in the endpoints at least, right? -2 and 3. But I might want to plug in some points in between as well, just to kind of get an idea for what's going on. In fact, I think I'm going to plug in every whole number. So I'll plug in -1, 0, 1, 2, and 3. Just so that I can get a sense for what's going on. So if I plug in -2 now here, -2 squared is 4. 4 minus 3 is 1. If I plug in -2 here, 1/2 times -2 would be -1. And so I get the point -1, 1. Right, so I'm going to plot the point, or sorry, not -1, 1, 1, -1. So I'm going to plot the point 1, -1. when t equals -1, I'm going to have -1 squared is 1, and 1 minus 3 is -2. And here I would get -1/2. So I have -2, -1/2 as another ordered pair that I'm going to plot. And so on and so forth for the rest of them. So moving a little more quickly, here I would get the point -3, 0. Here I would get the point -2, +1/2. Here I would get the point 1, +1. 1, +1. I was going to say 1/2, but no, it's just if I'm plugging in 2, I get 1. And if I plug in 3, 3 squared is 9, minus 3 is 6, and 3/2. Right? So these are the points that I'm getting. So let's go ahead and plot these. So I've got the point 1, -1, -2, -1/2, -3, 0, 1, 2, 3, -2, 1/2, so -2, 1/2. Okay, and then I've got 1, 1, 1, 1. And then I've got 6 3/2. 1, 2, 3, 4, 5, 6 3/2 right there. Oh, this is weird, right? In what order should I connect the dots? Well, I should connect the dots in increasing order of t, right? So when t was -2, I was starting right here. Then when t was -1, I moved this way, and then this way, and then I curved back around, and then curved around some more. And I'm not going to put arrows on the ends here because we were only supposed to graph the function between from t equals -2 to t equals 3. So this is the entire function. I could have drawn it a little better. It's supposed to be a parabola, right? Now it says to, oh, that's beautiful. Now it says to indicate the orientation. The orientation is this way, so we're moving in this direction around the curve, right? So there's the orientation of that curve. Okay, so that's that one. Here's another one. Okay, I'll let you pause the video and see if you can work this one out on your own. Okay, here's my solution. We just want to graph this over one period of t. So I might plug in the usual suspects. Starting at 0, I'll plug in 0. Well, let's just do the quadrantal ones, and then we'll come in and fill in some more if we need to. I'm going to plug in 0, pi over 2, pi, 3 pi over 2. And like I said, if we need to come back and fill in some more blanks, we'll do that. So if I plug in 0 for x here, cosine 0 is 1. 5 times 1 is 5. So I get 5. Sine 0 is 0. So I get 0.50. If I plug in pi over 2, now I get 0 and 5. If I plug in pi, now I get cosine pi would be -1. So this is -5. Sine pi is 0. And if I plug in 3 pi over 2, cosine 0, sine is -1, so I get -5 there. Well, that's probably not enough information to see what this is, but let's see, 1, 2, 3, 4, 5. 0, and then 0, 5, 0, 1, 2, 3, 4, 5. And then I've got -5, 0, 1, 2, 3, 4, 5. And then I've got 0, -5, 1, 2, 3, 4, and 5. So, you know, obviously we're moving around in sort of a counterclockwise direction. The only question is, you know, we don't know exactly what happens, right? It could look like a little, like diamond type thing. I mean, we really don't know. So I guess we should probably plug in some points in between just to get a feel for what's going on. I'm going to plug in pi over 4. If I plug in pi over 4, cosine pi over 4 is root 2 over 2. And 5 times root 2 over 2, let's see. 5 times root 2 over 2 is about 3.5. So I get about 3.5 here. And this is going to be the same since sine of pi over 4 is also root 2 over 2. So those are both about 3.5. So 1, 2, 3 and a half. 1, 2, 3 and a half, right about there. I have a feeling the same sort of thing is going to happen in the other quadrants, right? If I plug in 3 pi over 4, cosine is going to be negative, but it's still going to be, the absolute value is still going to be about 3.5. So it can be about negative 3.5. Sine is still going to be positive, so this one's still positive 3.5. So 1, 2, 3 and a half, 1, 2, 3 and a half, puts me right there. So I think I can guess what's going on now. 1, 2, 3 and a half. And 1, 2, 3 and a half. Okay, this has got to be pretty much a circle, right? Looks like a circle. So I'm thinking it's moving kind of in this way. And the direction of the circle is counterclockwise. Okay, so we're moving counterclockwise around this circle. And that's pretty much all there is to it, right? So that's how we graph parametric equations. Of course, one of the other things that we want to do besides being able to graph these things is to be able to convert between parametric form and rectangular form. So if we want to go from parametric to rectangular, usually the way to do that is to solve one of the coordinates for t and then plug that into the other coordinate. So that's what we'll do in that's what we'll do in a lot of cases, but anytime there's a trig function involved, then that's probably not a good way to go about changing it to rectangular form. So just keep in mind that what you're trying to do is you're trying to eliminate t, and you're trying to end up with an equation that's just in terms of x and y. So when we have trig functions, we'll try to make some clever uses of identities, right, to get rid of t, the parameter. So let me just give you a couple examples of this idea. So this one says eliminate the parameter to obtain a Cartesian equation of the curve, and we've got this thing here. Sorry. So like I said, the strategy, if you're dealing with something that doesn't have trig functions in it, then the strategy is usually to solve one of the equations for t. Now, I could solve this one for t, but then I'm going to have, you know, t is when I end up taking the square root, right? I'm going to get like t is plus or minus the square root of some nasty thing, right? X plus 3. I don't really want to have to deal with that, so I'd rather just solve y for t. I think that's a little more straightforward. So if y equals 1/2 t, then that means t equals 2y. And now I can take that and replace the t in my x equation with 2y, and that will eliminate my parameter, right? So in other words, you know, x is t squared minus 3, but I just figured out that t is the same thing as 2y. So this is just 2y squared minus 3. That's 4y squared minus 3. And there you go, right? There is our rectangular equation. And you can see that it is, in fact, a parabola, right? By the way, I should have mentioned, right, this is the same example as example 1a that we graphed. And you can see now that it is, right, it really is this parabola, right, that we were looking at before. Okay. So that's that. Here's another one. Now this one has some trig involved. This is the same as example 1b, which we are assuming is a circle. But let's see if we can change this into rectangular form to sort of verify that it should in fact be a circle. So in this case, we've got these trig functions. Usually a good set of identities to make use of would be the Pythagorean identities. So if x is 5 cosine t, then x squared would be 25 cosine squared t. And similarly with y, so then I'll have a cosine squared and a sine squared. I know that if I add those together, I'm just going to get 1, and that will eliminate my t's. So that's exactly what I'm going to do. I'm going to say, all right, well, x squared is 25 cosine squared t, and y squared is 25 sine squared t, and therefore x squared plus y squared would be 25 cosine squared t plus 25 sine squared t. Okay. Does that make sense? Well, you can't answer that question, but that's the idea, right? So x squared and y squared. Now, I can factor out a 25. And cosine squared plus sine squared is 1. So I get x squared plus y squared equals 25. That's my equation, and hopefully you can recognize that that is in fact a circle, right? It's a circle centered at 0, 0 with radius 5. And that's exactly what we drew, right, on the previous page. Okay? So that's how those things go. Here are a couple more examples. So go ahead and pause the video, see if you can work out this one. So see if you can change this into a Cartesian equation, a rectangular equation, and then see if you can identify the curve. And then we'll look at these curves in Desmos once we're done with these 3 examples. Okay, so now here's my solution. I guess I should mention, like, here I'm just writing the outputs as an ordered pair. So instead of saying x of t equals tan t and y of t equals secant t, I just wrote it as an ordered pair. But it should be pretty clear. Okay, x is tangent t and y is secant t. And now I'm going to do the same thing that I did on the previous example with Pythagorean identities and all that. So I'm just going to go ahead and say, if x is tangent t, then x squared is tangent squared t, and y squared is secant squared t. And then I can make use of a Pythagorean identity, right? So for secant and tangent, we have tangent squared plus 1 equals secant squared. Another way to say that, so here's just a little scratch work. So if tangent squared theta plus 1 equals secant squared theta, then 1 equals secant squared theta minus tangent squared theta, right? So in other words, I'm going to say y squared minus x squared equals secant squared t minus tangent squared t. And secant squared t minus tangent squared t should just equal 1. So I get y squared minus x squared equals 1. Now you may have done that a little differently, and that's okay. As long as you ended up here, right, you should end up with the equation y squared minus x squared equals 1. It says to identify the curve. Now this requires you to think back to your conic section days back in your college algebra class. But this one should be a hyperbola that opens up and down, right? So this is a hyperbola. right, and it opens up and down. Okay, so that's that one. Part B, give the video a pause, see if you can work this one out. Okay, so here's my solution. So x is 1 minus cosine t. Y is sine squared t. We need to figure out how to get these things, how to eliminate the parameter here. I know that I can think of sine squared t as 1 minus cosine squared t. That 1 minus cosine squared t, that might be useful. I'm not sure. Oh yeah, that'll be useful. So here's what I'm thinking. I'm thinking what I'm gonna do is move the 1 over. I'm going to get x minus 1 equals negative cosine t. And that'll allow me to solve for cosine t. So then I can say 1 minus x is positive cosine t. Okay, so now I can plug that into this top one, right? Because I can say, well, if y equals sine squared t, then that means that y is 1 minus cosine squared t. Well, I know that cosine t is 1 minus x. So this means that y is 1 minus x squared. Right? Do you see that? Because cosine t is 1 minus x. So cosine squared t is 1 minus x squared. Right? And now this, notice, is an equation where you've eliminated t. So you've done what you set out to do. Again, you may have done that differently, and that's okay. But let's clean this up a little. So I'm going to get y equals 1 minus, here we're going to have 1 minus 2x plus x squared. Distributing that negative and canceling like terms, I'm going to have a negative x squared plus 2x. So I'm actually just going to write that 2x minus x squared. That guy is a parabola, right? That's a parabola for sure. Okay, so there's that one. Oh, so I guess I should write down, right? This is a parabola, since we were supposed to identify the curve. Okay, so that's that one. And then part C. Oh, that looks a little rough. I don't know. Maybe not. Give the video a pause. See if you can work it out. I'm going to sit here and try to figure out how, how I'm going to do it. Okay, so this one, unlike the previous one, right, in part B, I knew that I could rewrite sine squared as 1 minus cosine squared so that I could relate sine and cosine together somehow. This one's a little trickier because I don't have sine squared and cosine squared. I just have sine to the first and cosine to the first. So I think I'm going to have to do like I did in part A and square both of these equations so that I can try to figure out a way to relate them. Now, before I do that, I think I'm going to want to move the 3 over. So because if I, well, let me write this down, right? So I have x equals 3 minus 2 cosine t, and I'm thinking if I square it the way it is now, I'm going to get a cosine squared, but I'm also going to get a cosine. And same thing with this one, right? It's y equals negative 1 plus 5 sine t. If I square it the way it is, I'm going to get a sine squared, which is good, but I'm also going to have a sine to the first, and that's not so good. Because it's not easy to relate cosines and sines. It's easier to relate cosine squareds and sine squareds. So, so I'm going to move the constant term over and say x minus 3 equals negative 2 cosine t. Then I'll square both sides. And Same thing here. I'll say y plus 1 equals 5 sine t. So y plus 1 squared is 25 sine squared t. Well, this is no good because I guess I should take it one step further and just go ahead and solve for cosine squared and sine squared so that I can add them, right, and get 1. If I add 4 cosine squared t plus 25 sine squared t, then I can't factor out anything in order to combine cosine squared and sine squared to get 1, right? So I'm going to divide by 4 on this side. And on this side, I'm going to divide by 25. And then I'm going to relate them. I'm going to relate these two together. So, so I can say now cosine squared t plus sine squared t equals x minus 3 squared over 4 plus y plus 1 squared over 25. And now this thing equals 1, and so I've eliminated the parameter, right? So I get 1 equals x minus 3 squared over 4 plus y plus 1 squared over 25. And there you go, right? That's my equation. We usually write this the other way around, right? We usually write x minus 3 squared over 4 plus y plus 1 squared over 25 equals 1. As our final answer. But there you go. This is an ellipse, right? This is an ellipse. To further convince ourselves of these things, let's take a look at these in Desmos. So Desmos will do these parametric equations. You just have to enter them as ordered pairs the way that I did. So I'm going to say f of t equals, for part A, it was tangent t, comma, secant t. Well, maybe it doesn't do them. I thought it did. Oh, I know that it used to do this. How do you do a parametric equation in Desmos? Parametric equation Desmos. It's as easy as plotting an ordered pair. Instead of numerical coordinates, use, I'm assuming they're going to say use the equation. That's what I did. Maybe I just need to get rid of the function notation and just say, yep, there you go. So I just needed to get rid of them. Well, anyway, let's do this from negative 100 to positive 100. And sure enough, you get this hyperbola, right? You get a hyperbola just like we thought you would. A hyperbola that opens up and down just like we thought we would. So that one's kind of cool. Same thing with the next one. We'll do with part B, it was 1 minus cosine t, comma, sine squared t. That's that one. And, you know, you have to adjust the limits here. And again, I'm going to say negative 100 to positive 100. And, yep, a parabola. Okay. It's not a full parabola, though. It stops right there and right there. And I'm assuming that's because sine and cosine are bounded, right? Sine and cosine live between negative 1 and positive 1. So something about the way you combine them means that you're never going to get something less than 0. And so these branches cannot continue. Anyway, and then part C. And we're guessing this one was an ellipse. So let's see. 3 minus 2 cosine t, comma, negative 1 plus 5 sine t. Well, that doesn't look like an ellipse, but maybe if I make this negative 100 to positive 100, there we go. Yeah, we get an ellipse, sure enough. An ellipse centered at 3, negative 1, and then from that point you go left and right 2, up and down 5, right? That's what this equation is. That's what this equation is suggesting you should do. Anyway, so that's that. I think they're kind of fun. Okay, so that's how we go from parametric to Cartesian, or in other words, rectangular. To go the other way around, to go from Cartesian or rectangular, right, to parametric is called parameterizing a curve, and it's actually a lot easier to parameterize a curve than it is to unparameterize a curve, in my opinion. The most simple way to parameterize a curve is to let x be t, and then let y be whatever function of t you started with. Okay, so for example, if our original function were x squared plus 1, then a parameterization would be t comma t squared plus 1. Okay. That said, there are infinitely many ways to parameterize a curve. So what I want to do on these last two examples is give two parametric representations for each function. So we'll start off with f of x equals 3x plus 2. So here's one parameterization. We can say f of t is going to be t comma 3t plus 2. So there's one way to parameterize the curve. Okay. To do this another way, well, you can really plug in anything you like for x, right? You could plug in like 2t, or you could plug in, oh, I don't know, like t squared plus 17. I mean, whatever you want. You can plug in whatever you like for x. I'm going to make it so that our y coordinate is just t. So in order to do that, I would have to get, I think I would have to do, if I do this, what would it have to be? 1/3 t plus or minus 2/3, I think. So if I let, I'm just playing around. I mean, but I'm going to say let x be 1/3 t minus 2/3, and then if that's the case, I would get y equals 3 times x plus 2, and that would be t minus 2 plus 2, which would be t. So another way to parameterize the curve, maybe I'll just say it like that. So this is f1, f2 of t, I could say would be 1/3 t minus 2/3, comma t. Anyway, that was maybe a little bit complicated, but I just wanted to see if I could challenge myself and get a y coordinate of t. And you can, but like I said, you could use anything you'd like. You could say, so I'll give you a third one, just for the sake of, I don't know, clarification, right? But you could use anything you like for t. You could say, let x be 2t, right? And then y would have to be 3 times 2t plus 2, right? Because y is 3x plus 2. And so then you'd get y equals 6t plus 2. And f3, so our third function, would just be 2t comma 6t plus 2. And all of these parametrizations are going to give you the same curve. And in fact, I can prove it to you. We can look at Desmos. So looking at Desmos here, the original one we came up with was t comma 3t plus 2, right? Oh, maybe let me fix these boundaries. So let's go from negative 100 to 100. Okay, so there's that one. Now here's the second one we came up with. It was 1/3 t minus 2/3, comma, t. So this one's in red, but you'll notice that it's the same line here. If we go from negative 100 to 100, then yeah, it covers exactly the same thing. So hopefully that convinces you. I mean, we could do the last one just for good measure, 2t, comma 6t plus 2. But they're all parameterizing the same line, right? They're all parameterizing the same thing. This time it's in blue. And yeah, there you go, right? So you can see it. But that's that idea. Okay. So one more example, and then you're done with the class. I mean, you still have to work out some homework problems, but see if you can work this one out on your own. See if you can find 2 parametrizations for this one. Okay, here's my solution. So the first one, I'm just going to say our g1 of t, I'm going to say is t, comma, t minus 2 squared plus 1. So that's the easy one, the boring one. Okay, for a second one, you could choose any value of t you like. What I mean is you can let x be any value you like. I'm going to let x be t plus 2, because then I think you get something nice kind of happen. Right? So if I let x be t plus 2, then y would be t plus 2 minus 2 squared plus 1. All right, it's x minus 2 squared plus 1. So that's going to be just t squared plus 1, which is kind of nice, right? So then my second parameterization is going to be t plus 2, comma, t squared plus 1, which I think is actually nicer than the easy one. The easy one's, you know, not so nice to look at. This one, if you give it a little more thought, you can come up with a slightly nicer representation. But both of these are going to parameterize that parabola. Okay. So that's that. That's all I want to really say about parametric equations. And it's been a pleasure. So good luck with the rest of the semester and your future endeavors.